Okay. Thank you for the introduction. So yesterday we defined the Okounkov body. Okay, and we studied the dimension and the volume, and so what they mean. So in the big, so actually we also defined this limit. Okay. So this dimension is the numerical Ithaka dimension, and the volume, Euclidean volume. Volume corresponds to this augmented restricted volume, so where V is y n minus k. Okay. And yesterday I forgot to add one more result, but so in the big case, the Okounkov body was a numerical object. So in the big case, so D are big. Okay. D prime for any flag, if and only if D is numerically equivalent to D prime. But actually, I forgot to add this result, but this actually holds for pseudo-effective case. So it's pseudo. So if you replace this by limiting Okounkov. So this is also some extension of the Lazarus-Musata's result. Okay, so in some sense we studied some global aspect of the Okounkov body. Today we study the local positivity. Okay. Okay. So let's recall the examples. Back to the example. Yesterday's example. We saw three examples. So this is this and this and this. Okay. So this is x is p2, and the divisor is just a line. So actually the flag is not important here. And here x is the blow up of P2, and pi is the blow up, and here divisor was pi pullback L. And here the situation is the same, and divisor was pi pullback L plus some E is an effective divisor. Okay, so we saw these three examples. And, sorry.
But in all those three examples, delta U can say the usual, right?
Precisely what?
So you have delta and you have delta U, right?
Delta, what's delta?
You have this equation of delta U. And then you have the usual delta. Am I right that in all three cases, delta is the same?
I'm sorry, what is delta? Delta.
Usual. Like
delta, yeah.
And then you have this delta mu, right?
Yeah.
And is it all the same in all three examples?
In the big case, yeah. So if D is big, there is no difference. You don't need to take the limit.
Sorry, particularly in the theorem, one can replace delta U by delta.
I'm sorry. So in this theorem.
Yeah, you would drop this U, right?
In the big case, yeah, you can drop.
Yeah, I mean the theorem.
Yes. Yeah. But of course, even if the divisors are pseudo-effective, you can also consider this Okounkov body, but this thing is not numerical when the device is pseudo effective. So to recover the numerical property, you actually have to take the limit. So this is the point. Okay. Okay. So we saw these three examples, and I explained yesterday, but this is not NEF. This is NEF, not ample, and this is ample. Okay. So if the divisor is ample, it contains some neighborhood of the origin. If it's only NEF and not ample. If it's not ample, then it only contains the origin. And if it's NEF, it doesn't even contain the origin. Okay. So we will make this observation more precise today. Okay. So this is what we will do first. Okay. So to make the statement more precise, we have to define the asymptotic base loci. So we are using only Q divisors. Okay, so let's have Q. This is Q divisor. Okay. And the first, let's record the stable base locus. Stable base locus is the base MD. So because this is a Q divisor, if you multiply some integer, it becomes an integral divisor. And you can talk about the base locus in the usual sense. Okay. So MD integral. Okay. This is called the stable base locus. Okay. But so it is when, if you read the Lazarus positivity book, so it says that this is not numerical. Okay. So actually we want everything to be numerical. So we define the following two base loci. Okay. So the first one is called the augmented base locus. And the B minus is called the diminished base locus. Okay. So this is defined as, so these two are dual to each other in some sense. So this is the intersection of SB, B minus A. So this definition actually works for R divisors, but we can, let's assume that D is a Q divisor. Okay, so A is ample. Okay, A is ample. And this is the dual. So here we take intersection, here we take the union. So SB, and here we subtract the ample divisor. Here we add ample divisor. Okay. So these are called the augmented base locus and the diminished base locus. Sometimes it's called the restricted base locus. And so here are some basic properties. So it seems that these days it's more common to use these base loci than this, because this catches more subtle properties of the divisor D. So asymptotic behavior of D. Okay. So there are actually many properties. So I mentioned only a few. So B plus is statistically closed. This means it only has finitely many components. So actually we took the intersection over infinitely many ample divisors, but actually this is equal to D minus A for some small ample A. Okay, so you can just fix ample divisor here. And you also expect that B minus is Zariski closed, but actually it's not Zariski closed in general. It's not. Okay, so this is so there. So he gave an example of this base locus, which is not Zariski closed. Okay, so this can have infinitely many components. Okay, so and the other one is B plus is empty if and only if D is ample, and B minus is empty if and only if D is net. Okay, so sometimes this is called non-net locus, non-ample locus, and sometimes this is called non-net locus. So it's easy to check. This is very easy exercise. Okay, so actually, yeah, there are many more interesting properties. Okay. Okay. So using these base loci, we can formulate a theorem which makes this observation more precise. Okay. So theorem. B is a divisor on X, and the following are equivalent. So 1, 2, 3. X is not in B plus. Let's have a theorem about B minus first. B minus. So this is D is nef at X. So this is not the official definition, but you can say D is nef at X. Okay. This is non-nef part of D, and X is not contained in here. So D is nef at this point. Okay. And the next one is, as I said here, so there exists a flag with the flag is a sequence of subvarieties whose coordination increases by 1. So the last one is a point. So Xn is a point. Is a point given by this one. For there is a flag with the last one at X, such that so the origin is contained in So let's assume D is a big divisor from here. So even if actually you can also put a lim here, but you can for convenience let's assume D is a big divisor. Okay. So everything works for pseudo-effective case if you put lim here. Okay. And the next one is for any y the same. Okay, so origin is because this is an object in R. The dimension of the variety is n, so this is n. Okay. So So as a corollary to this theorem, we just need to consider the case where this is empty. Then you get the full statement. Okay. So also the following are equivalent. Let's say D is nef. 2 for any the origin is contained in D. 3 for any point in X, there is Y with X such that the origin is contained in. Okay. So you just consider the case where D is nef. So because D is nef, B minus D is empty. Okay. So in this case, so in this example, we consider the one particular flag, but because this is nef, this is the case for any flag. Okay, this is true. This picture is holds. The origin is contained in the Okounkov body with respect to any flag. Okay. Because this divisor is nef. Okay. So here I state just key fact used in this proof. So it's also important fact. Okay. So first you define the asymptotic order. So X is a point, proof of theorem. So X is a point, then you can define the asymptotic order of the divisor. D, infimum of the order of X, D prime, D prime, effective. So you can just have Q. Okay. So this is not just the usual order. So you consider all the effective divisors, Q linearly equivalent to D, and you take the limit. Then you get asymptotic order. Okay. So this is the case when D is big. But if D is only pseudo-effective, then you define order of XD as the limit of the order of X, D plus epsilon A. So A is some ample divisor. And epsilon goes to 0. Okay. So this is called asymptotic order. Okay. So key fact we use in this case is fact. It's actually theorem, but X is in B minus if and only if order of X D is okay. So we use this fact. So using this fact, it's easy to prove. So I'll just get main idea is this. So main idea is suppose origin is not contained in some Okounkov body. So this is the step for 1, 2, 3. So this is the main part. Okay, so suppose is not contained in the origin is not contained in this Okounkov body. Then the picture looks like this. So origin is not contained. So it must look like this. Okay. So it's away from the origin. So you can take some small epsilon neighborhood. Okay. So because mu I d prime is order x d prime. So we are assuming 1, right? Okay, so assuming 1. So x is not contained in there. So using this fact, so before this, because we are assuming 1, and if you use this fact for any epsilon, there is an effective divisor d prime, which is Q linearly equivalent to this order of x, the order of x d prime is less than epsilon. Okay, so according to this fact, by okay, and we can also verify that this is smaller than, larger than or equal to mu I d prime. So yesterday we defined a function for effective divisors using the admissible flag. Okay, so d goes to mu1, mu2, and mu(n). So this is one of them. Okay, so we can actually prove this statement. Okay, it's easy observation. Okay, so anyway, so if the origin is not contained in the Okounkov body, it's completely away from the origin. So you can take the epsilon neighborhood. By using this fact, all the coordinates is less than epsilon. So this means we can find derivative point d prime arbitrarily close to the origin. Okay. So this means 0 must be contained in the Okounkov body. Okay. Because in the construction of the Okounkov body, we have to take the closure. Okay. But we have found a point which is arbitrarily close to the origin. So here we have a contradiction. Okay. Okay. So this is the main idea. So we just sketched the proof for this direction, but this is the easy part. Okay. So it's a formal calculus on the convex bodies. Okay. So the point is, if the divisor is in F, for any flag, the origin must be contained. This is the conclusion. Okay. Okay. So we have the similar statements for B plus. Also sometimes people ask why you put minus and plus here, but of course this is bigger. So I assume this is why they put plus sign and minus sign. Okay. And the stable base locus is between here. Okay. Okay, so now about B plus. Here. B plus. So D is a divisor on X, and again, the following are equivalent. One. So its statement is similar. Just replace this by plus and this by the neighborhood of the origin. X is not contained in D plus. So we can also say D is ample at X. But okay. And 2, there is Y prime, the flag with Y n at X, such that so our domain is always in this, the first, the positive coordinate. So if I say neighborhood, it of course means this neighborhood. Okay. How do you such that D contains some neighborhood of the origin. Okay. So as I said, this means this is so by neighborhood I mean this one. Of course, it cannot contain the whole neighborhood. Okay. 3, for any with X, and the rest is the same. And here again, as a corollary, you just consider the case where this is empty, which means equivalently, if you just assume D is ample, then you get the statement we need. The following equivalent. X is D is ample. 2, for any flag, the origin is contained in I mean the neighborhood, some neighborhood. Of the origin is contained in this, and 3, for any point in X, there is Y, such that some neighborhood of the origin is contained. Okay. So I just erased, but we had this picture. Okay. So here in this example, we only considered one particular flag, but actually this is independent of the flag. The neighborhood is always contained for any flag. This is what this corollary says. Okay. So here again, I just sketch the main part. So proof. Just sketch. Over here again, 1, 3. Let's sketch of 1, 3. This is the main part. The rest is again not too difficult. So the idea is use induction. Okay. So first step is so you just verify that X is also contained in the Y1. So if you restrict D on Y1, this becomes a divisor on Y1, and so your variety is smaller than X. Okay, here you use the induction. And step 2. So you also verify that this is equal to y1 dot d y1. Okay? So this means that your Okounkov body will look something like this. Okay? And you first check that x is also contained in this augmented base locus. And this means you let x1 equals 0. You just restrict the picture. So this means you only consider this part. So this is x1 axis, x2 axis, and x3 axis. Okay, so if you restrict onto this this coordinate, then you get this picture. Okay, and then this is equal to this. Okay, so and by induction, this must contain the neighborhood of the origin. Okay. This part. So by induction, this section must contain the neighborhood of the origin. Okay, and in the next step, step 3, find a derivative point here. Okay, any point is okay on x1 axis. Okay, so we know that the Okounkov body is convex. So Okounkov body should contain this neighborhood, and it also should contain this point. So that means if you consider the convex hull of this, this neighborhood must be contained in the original construction, original Okounkov body. Okay, so let's say this is x convex hull of x and this neighborhood must be contained in the original Okounkov body. Okay. So this proves this direction. Okay. Okay. So once you have these steps, it's not too difficult. Okay. Okay. Yeah, so this is about B plus, and we also had B minus. Okay. Any questions? Okay. So now we want to focus more on the local positivity. So now we restrict our divisor to be ample. Okay, for ample divisor, you can define something called Seshadri constant. It's a very important notion in algebraic geometry. And you can also say something, you can also measure the Okounkov body, the Seshadri constant from the Okounkov bodies. Okay, so definition. So D is an ample divisor. Okay, so this is the Seshadri constant. So this actually measures how ample this is at a given point. And X is a point, So the notation for this is epsilon dx, and this is, so there are few equivalent definitions, but we need only two. So this is, the first one is, of t pi d minus te is nef. So as usual, pi is the blow of x, okay, and e is the exceptional divisor. Okay, so this is called the Chadel constant, and you can also define this using curves going through this point. This is the infimum of all the irreducible curves passing through the point x. This is C and D, C. Okay. Okay. So this measures how ample this divisor is at the given point. Okay. So this is called the Chadel constant, and you can also define something similar for big divisors, because as I said, I explained this yesterday. So the limit of ample divisor is n, and the limit of big divisors is pseudo-effective. Yeah, so for big divisor, you can also measure how big the divisor is at a given point. Okay, so actually this doesn't have fixed name; it has many names. So Nakayama constant. Some people call it Fujita Nakayama constant. Some people call it Fujita type constant, pseudo-effective threshold, and it's many names. Okay. So for this, these are big. So like in this case. Okay. So usually this is denoted by mu, and this is t pi full vector d minus te is, so you can put either big or you can actually put pseudo-effective part. Okay. Any questions? Okay. So you want to see how these constants are hidden in the Okounkov bodies. Okay. So to state the result, we need some more preparations. So like in this case, if you want to measure the amplitude of the given divisor d at x, it's somehow natural to blow up, consider the blow up. Okay, so need to consider the Okounkov bodies of pulvex. Okay, so pi pulvex. Okay, so we need to look at the Okounkov bodies of this pulvex as we did here. Okay. So, and also we need to use the admissible flags of certain kind. Okay. So pi blob of x, so x, and we have the exceptional divisor, which is isomorphic to Pn minus 1. And so we need to use some certain flags on this model, not on here, because we are going to construct the Okounkov body of the pullbacks. The divisor is in here. Okay. So how do we do this? So we start from this divisor. Okay, so as for y1, you put e. For y2, you just cut it with the hyperplanes. Okay, so this is e hyperplane. So let's put 2. Okay. So this is isomorphic to Pn minus 1, Pn minus 2, Pn minus 3, and so on. Okay. Y3. Let's just put E intersection H2, H3, and so on. Okay. And again, last one is a positive. Okay. And this type of flag is called the infinitesimal flag. Flag over X. There's a hyperplane. Yeah. So the image of the whole flag is just X. So everything collapses to X. Okay, so this is called the infinitesimal flag. So we are going to use this flag. And we need one more step. So as we saw in the P2 case, we had this blob of P2, and this line, you pull back the line, and we study the Okounkov body of this pullback, and the shape looked like this. Okay. But actually, this is the case in general. So something similar happens for higher dimensional case. So that means if you pull back any divisor and you construct the Okounkov body with respect to the infinitesimal flag, then your Okounkov body lies somewhere here. Okay. So for any ample divisor D on X and infinitesimal over X, the Okounkov body So your Okounkov body always lies somewhere in R plus E1. So EI is a standard, the normal vectors in Rn, plus R plus E1 plus E2 plus R plus E1 plus E2 plus En, E3 R plus E1 plus En. So in dimension 2 case, so actually it's you don't need to sample case. Okay, anyway, so in dimension 2 case, the Okounkov body of the pullback is always a subset of here. In dimension 3 case, so this means this and E1 plus E2. So this is and E1 plus E2 plus E3. So it's a cone spanned by these three rays. Okay, so the Okounkov body is a subset of this cone spanned by these three axes. Okay. So now using these two, this fact and using this infinitesimal flag, we define this invariant delta minus 1. So it's called the inverted simplex. So you know what the usual simplex is, but this is the variation of the simplex. So in dimension 2 case, this is the standard simplex. But inverted simplex means this one. And here also, the inverted simplex in dimension 3 is the convex full of the origin, and here, here, and here. I mean, origin and these 3 points. Okay? So this is a convex full of the origin, E1, E2 plus E3, E1 plus E2 is 2. E1 plus E2 plus E3, E1 plus En. I mean delta. So the size, the delta is the size. Delta. Okay. Okay. And now we can state the result. Okay. So actually, this is a theorem by Kronia and Lozovano. So this is, let's. So D is empty, and X is a point of X, and then the Society constant can be precisely computed using the Okounkov bodies. So this is so the delta of dx, and I will define what this is. This is the supremum of delta. The inverted simplex of size delta is contained in the Okounkov body of pi pullback D. and where so y is infinitesimal. So the simplest case is this one. So this was the Okounkov body, and so according to this, the Sechadich constant of d at x is equal to 1, because this size is 1. Okay. Okay. So in general, your Okounkov body may look like something like this. And the simplex inverted simplex function at x, the largest simplex contained in this Okounkov body is this one. Okay, so this number will be equal to the Sechadich constant. Okay. So if you blow up and consider the Okounkov bodies of the pullbacks, you can precisely compute the Okounkov bodies. But even if you don't blow up the point, you can have some nice estimate. So this is our theorem, CHPW. Okay. So myself and 3 other collaborators. So in this theorem, we don't blow up. We just use the admissible flags on the given variety. Okay. So this also has a nice estimate. So D is ample. And Y is any flag on X. Okay, so we don't blow. We don't consider the birational models. So D is ample, Y is a flag on X. Then we know that the Okounkov body of D with respect to Y contains some neighborhood of the origin. Okay, so it will look something like this. Okay, so I can define formally, but this one, the largest, the segment in the first coordinate axis is lambda 1. And this is lambda 2. And this will be lambda 3, and so on. Okay? So these edges tell you something about the Sechadich constant. Okay? So then minimum of lambda I is x, and so we have this estimate. So this may be weaker, but here you have to blow up. Here you don't have to blow up, but you still, if you blow up, you get the precise Sechadich constant. But if you don't blow up, you get these estimates. Okay. Okay, so So again, let's sketch the proof. And I also skip the boring, the technical part. So for the upper bound is actually easy. dx. The Caesar's constant was what? The infimum of dc multiplicity of xc. So where x is contained in c, right? But so in the flag, the first one is a prime divisor, and you continue, and the last one is a point. The last one before that is a curve. So this is a curve. So we use this curve. We put in here. Okay? So to get the upper bound, it's enough to prove that for any curve, So as I said, I will use this y n minus 1. Okay. So this is d y n minus 1 multiplicity x y n minus 1. Okay. Because y n minus 1 is a curve. And in the yesterday, when you constructed the Okounkov body, so the admissible flag should satisfy some conditions. So one condition was each yi must be smooth at the point. Okay, so this denominator is actually 1. Okay, so that's just the that's one. Okay. And we know that this is actually y n minus 1. So the segment in the last coordinate, this is actually equal to the intersection number of d and y n minus 1. Okay. So here we have to use some fact, but here we use this fact. This is not contained in d plus d, but this is empty. Okay. So whenever you have this condition, you get this equality, but this is already empty, so it's obvious. Okay. Okay, so this is how you get upper bound. And the lower bound is also easy. This is just the induction. Okay, so let's start from this minimum. Lambda I. So I is from 1 to n, right? And this is actually smaller than or equal to the minimum of lambda I from 2 to n, right? So if C is contained in Y1, yeah, so if let me erase this. So this is 1, so it's erased this. Okay. So to prove the lower bound, we have to for lower bound. It's enough to show the minimum of lambda I dc multiplicity of x. Okay, for any curve. Yes. So if we can show this, we obtain the lower bound. Okay, so first we assume that C is contained in Y1. Then we can restrict everything on Y1. Okay, so by induction, so this is smaller than this, and by induction, this is actually equal to this is less than or equal to dy1 C multiplicity of xc, but this is just equal to multiplicity xc. Okay. So this is the case when c is contained in the first component of the admissible frame. Okay. So, but of course, you have to treat the case where this is not contained in here, but this is a very technical part, and I will not cover this part. Okay. But other than this part, it's very, very basic. It's not too difficult. Okay. And I will show you some applications. So even if we only obtain this lower bound and upper bound, in some cases it's useful. Okay, so some little application. So we can, it's not really a big theorem, but we can characterize the Pn using the Okounkov bodies. Characterization of Pn. Okay, and theorem. So X is a smooth funnel. Okay, so minus K is X is empty. Okay, so the following are equivalent. So Pn is the simplest funnel variety in some sense. So the Okounkov body of this Kx must also have the simplest structure. Okay, so 1x is Pn. What is the simplest Okounkov body you can have? It's just a simplex. Okay, so your Okounkov body of K minus Kx is actually simplex of some size. Here is y1, so still. This is standard. So this is standard simplex. Simplex in Rn. Okay, 3. Is contained in. Actually, you don't need this third one, but I just added for convenience. Okay, so this theorem says if the Okounkov body of minus Kx has the simplest structure, which is the simplex, then your funnel variety must be Pn. Okay. So this is quite easy. So from 1 to 2, because you can assume x is Pn, so minus Kx is minus n plus 1, some hyperplane. Okay? So plus, yes. Okay. So if we can construct the Okounkov body of H, then you can just rescale it by n plus 1. Okay, but so take y1 as H, as we did in the infinitesimal case. You just successively take the intersection with hyperplanes. So n y2 is H prime and so on. Okay. Then it's easy to see that this is just a simplex. Okay. So there, and now you multiply by n plus 1, and this is the Okounkov body of minus k. Okay. And of course, 2 to 3 is obvious, and 3 to 2 is the most unobvious part, but so 2 to 3 is obvious, and 3 to 1. For this, we use this theorem by Zhuang, one of Collard's students. So he proves that if n if the Shadari constant, so the situation is the same. X is Fano. So later he proved that this is true for KLT, but it assumes this is smooth Fano. Then X is here. Okay, for some X. Okay, so we use this, and so we are assuming 3, and we want to use this one. So if you apply this theorem to this situation, the minimum is, all the lambda i's are the same, and the lambda I is actually n plus 1. So according to this theorem, n plus 1, so minimum of lambda I. Actually, all lambda i's are the same, so this is n plus 1, n plus 1, b plus x. So it's even bigger than n plus 1. Okay, so this is x is here. Okay. So for Fano variety, for Pn, the Okounkov body for the anti-canonical divisor with respect to some flag must be the rescaling of the simplex. Okay, has the simplest structure. Are there any questions? So this is about the Shadari constant. Okay, Shadari constant is measured by the inverted simplex, the largest inverted simplex, or the simplex contained in the Okounkov body. Okay. So I believe that you can also compute this. Pseudo-effective threshold by studying the simplex which contains the Okounkov body. Okay. So the question is, what about this one? And actually, the answer is yes. So this is a result by Dominic. 그러냐? Also, no, those one. McLean, Temple. So I can't explain all the details, but for X, they define something called Okounkov function. Whose domain is the Okounkov body, and the image is R. Okay? And they prove that this is actually equal to the maximum. Maximum of how do you write X? Okay. So to define Okounkov function, you need many steps. So I cannot define this today, but so this is how you can recover this Nakayama-Fujita type constant. But so as I said, I believe you can recover mu dx from the structure. Okay, so this has not been done yet, but I believe you can also do this. So if you are interested, you can think about this. Are there any questions? There is no question, then the leader know about this. So I will do more about this tomorrow, but let's start some. So more local positivity. So we know 4 big divisors. 4 big divisors. D, Y, no. X, D, sorry. D is numerically equivalent to D prime if and only if the Okounkov bodies are always the same. So we know this fact. Okay. Okay. So we want to see this more locally. So that means, what if we fix the base? If we consider the admissible flag with a fixed base, then what do you have on this side? Okay. So the question is, why with so fixed base? So this is fixed. Okay. Any guess? So this means D dot C is D dot C. So C is any curve. So intersection numbers are always the same for any curve. Right? So you may want to say that DC is equal to DC prime for any curve C which passes through X. You may guess this is the answer, but this is naive. No. This is the wrong answer. I was going to say this is wrong answer. But this still defines D prime. Okay. Sorry. So even if you consider the curves which goes through some fixed point, there is no difference. So this is actually wrong. Okay. So this is not the answer. Okay.
I mean, you say that this is not equivalent to natural equivalent.
This is okay, but this is not equivalent to this. This is wrong because it still defines the same equivalence class.
So the cross should be...
Sorry. Sorry, I made you confused. So this is equal. So this equality is okay. But this is not equivalent to this. So sorry for the confusion.
The assertion to say that is correct.
So this statement itself is correct, but this is not equivalent to this. Which is strong. So this is stronger, yes. But even if you consider the curves through X, it doesn't strengthen the condition. Okay, so you need to come up with different notions. Sorry, I made you confused. Okay, and the answer was given by Roy Joachim, and I want to generalize it in higher dimension case. Okay, so here we have to use the notion of Zariski decomposition, and so maybe I have to finish. Sorry, yeah. Sorry, let me make this precise. So I want to find this. Okay. So your guess, actually, it's a wrong guess. D, C, D prime C for any curve C which goes through X.
So the more the second is wrong.
Second if. This is, yes, this is wrong. Because this is the same thing as this. Okay, so this naive guess is actually wrong. Okay. So to come up with the correct notion, we use the notion of Zariski decomposition. Actually, let's have it divisorial Zariski. So here is the definition. D pseudo effective. If and E is a prime device. Okay. And multiplicity. Order of E. D. So actually, I defined this for a point, but this time we have a divisor. So infimum of the multiplicity of E, D prime, D prime. So we are using Q divisors, so let's have Q. So if D is big, if D is not big, order of D is the infimum. The limit. Order of E, D plus epsilon A is M. Okay. So if D is big, then you use this infimum. But if D is not big and only pseudo-effective, you use this limit. Because pseudo-effective plus ample is always big. So you use this definition. Okay. And key fact is there are only finitely many E's such that order of E is I think this is fine. So there are actually finitely many prime divisors whose asymptotic order is positive. Okay. So now you collect all of these. There are only finite remaining. Okay, so this is the negative. Of D. N is order E. Okay. Because there are only finite remaining and these are positive. So this is a well-defined divisor. Okay. And the positive part of D is denoted by P. It's just D minus N. Okay. So here you have D equal P plus N. This is the divisorial Zariski decomposition. So, and this generalizes the Zariski decomposition in dimension 2 case. Okay. So in dimension 2 case, so if X is a surface, then this P will be in NEP. But in general, in higher dimensions, P is only movable. So in dimension 2, the Zariski decomposition is the same thing as the divisorial Zariski decomposition. Okay, and in dimension 2, P is NEP. Okay, but in dimension larger than 3, P is only movable. This means I already defined B minus. So this NEF means what? B minus P is empty. Okay, because this is non-NEF locus. But in this case, so what this does is you extract all the divisorial component has no divisorial component. Divisorial means codimensional one component. Okay. This is called the movable. Okay. And I forgot to state one property of B minus, but B minus has no isolated points. Okay. So it doesn't have a point. It only has curved surfaces and 3-4s and so on. Okay. So so what this does is, if you start from B minus, you extract all the divisorial components so that this becomes movable. So P. Okay. And I stated yesterday about the philosophy of having Zariski decomposition is you are given a divisor D, but if you have a Zariski decomposition like this, in many cases, you can throw away this negative part. Okay, all the positivities are kept in P. Cheshire constant, B plus, B minus, they are all contained in here. So in most cases, you can just throw away N. Okay? It's enough to study the smaller divisor. This is the principle. Okay, so I will recall a little bit about this tomorrow, and so using this notion, we can find the answer for this. Okay, so yeah, I stop here.